that. Also, remember yesterday's lecture video is posted if anybody needs to get into that for notes. All right, so we talked about, as we were wrapping up, I went into the fact that, and we're going to need 31016, so you might as well have it ready to go, which is the ampacity table. All right, just to read what this table says, it says ampacity for insulated conductors. Very important. There is another table that will deal with insulated conductors in free air, 31017. Free air meaning outside, no conduit, which conduits can, wires can be in free air for telephone line, not telephone lines, but lighting on, outside venues, stadiums, etc. Pole lights. So these are ampacities of insulated conductors with not more than 3 current carrying conductors in the raceway cable or directly in the earth. So this is something that we're going to come back to next week when we actually get into this Article 310. There's a lot to unpack here. We got to talk about all these insulations and what they mean. All these letters have a specific about the insulation itself and where you can use it and what it covers. But the other factor is that the amperage that you see down here for all of these conductors, whether it's aluminum or copper, whether it's THHN or THW or whatever it is, it's based off of the fact that we are not putting more than 3 wires in the raceway. 3 wires in the raceway is the cutoff point for this amperage. If you put more than 3 wires in a raceway, if you start to put multi-wire conductors together, then there is this other table here, 31015C1, where we have to adjust for more than 3 current carrying conductors in the conduit. This is the table that we're going to return to. But there's a theme to this, and the theme is the more wires you put in, and there is a specific thing about these wires, which is they are current carrying conductors. Load current carrying conductors. All right, not just current flow the way a lot of times you'll read that when you turn power on, flow or current is flowing through the circuit, yes. But it's not until you turn on the load that you get load current. All right, that's the big amperage that we measure with our amp meters. This is the amperage that we set breakers to protect the wires from. So the second you go into 4 wires, 6 wires, you can see it goes all the way up to 41 and above wires in a single conduit. The wire loses its ability to carry the amperage that's in 31016 by a factor of these percentages here. Because essentially what you're doing when you put more current carrying conductors in a space that is limited to be able to get rid of the heat, then 1, 2, 3, 4, 5, 6 wires start to generate a lot of heat. And so if the number 12 could hold 25 amps, as you get in, let's say for example 6 wires in this circuit, in this conduit, now it can only hold 80% of that. So 80% of 25, whatever that number comes out to. As I said, we're going to come back to this, so no notes here yet, although get an understanding of that, because as I backtrack now into the temperature correction factor, this takes on the same principles. All right, coming now over to the section here, which is sort of where we left yesterday. I read a little bit of it, mostly just to get us to the table itself. But I do want to go over a few things out of here just to point out. So the article itself, temperature limitation of conductors, meaning every conductor has a temperature limitation. It's going to be based off of the insulation of the conductor, but it says no conductor shall be used in such a manner that its operating temperature exceeds the designated type for the insulation. So THW rated for, THHN rated for a different temperature. We got different temperatures for different conductor insulation. Not many, it's only 60, 75, and 90. And if you look at 60 only has 2 wires in there. 75 has a good amount, and 90 has a good amount. In no case shall conductors be associated together in such a way with respects to type of circuit, the wiring method employed, or the number of conductors, that the limiting temperature of any conductor is exceeded. So we have to make adjustments. That's what it boils down to. The more we start to exceed certain temperature ratings, we have to now consider that for the conductor. Now, it sends us into the table, but I do want to read these 1, 2, and 3 from the informational note. All right, 1, 2, and 3 are telling us ambient temperature. All right, first of all, what is the ambient temperature? It's the temperature around the wires. Now, of course, these wires are going to be in a conduit, so the ambient temperature is the temperature inside the conduit. And as it says there, ambient temperature may vary along the conductor length as well as from time to time. So what are the things that can vary the conductor on the length? Well, let's say I'm close to a junction box. The wires here, closer to the junction box, are going to be experiencing less heat than, say, this is a 100-foot run of conduit, the dead center of that 100-foot run of conduit. Because there's not a lot of area there for this heat. This heat has to start to get out of that conduit. So at the edges, near junction boxes, near panels, one of the ways we like to call these points are pull points, a place where you can pull wire from. And this kind of covers everything that you can pull wire from. Junction boxes, panels, conduit bodies, termination points on machinery, transfer, well, you name it. If a conduit is landing there and we have some wires coming out of there, that is a place where I could pull wires from, so it becomes a pull point. So that would be, closest to a pull point, would be a place where the temperature was varying a little bit. All right, ambient temperature may vary along the length. Closer to a opening, less heat, dead center of that conduit, we got heat. All right, we got a lot more heat. As well as from time to time. What is time to time? Well, the load is on, the load is off. If the load is off and it's off for 24 hours, then those wires are cold. There's no heat on them. You turn on the load after, when you first turn on the load, not a lot of heat. As time goes by and the load current is running through the conductors consistently, you know what the point of considering it a continuous load becomes? 3 hours or more. So 3 hours or more is when we will start to experience, or the wires will experience, the most heat for the time. So length of the conduit, the time that the load's been on, these are going to be factors that change the ambient temperature that the wires are dealing with. All right, reading the other two, heat generated internally in the conductor. Now we're not talking about the conduit. Now we're simply talking about the wire itself. Inside the wire itself, where the copper is, it is experiencing heat. That's what they're talking about here with heat generated internally in the conductor as the result of, and they are giving us the correct breakdown of that current flow. It's load current flow, not just current flow. Current flow happens the second you turn on the circuit. Load current flows, and by turn on I mean flip the breaker. The load might be off, right? I got my breakers on, as are all your breakers in a house. They're all on. If the lights are off, nothing's running, we still have current flow to the circuit, ready to go. But we don't have load current yet. Load current is the one that starts to generate the heat. Now, fundamental and harmonic currents, that we don't need to get into that, but just suffice to say that these are currents produced by electronic pieces of equipment. Things like computers, networking towers, even ballasts for fluorescent lights produce this harmonics. And harmonics are just what we call a dirty sine wave. All right, the sine wave is usually a nice flow like that. When you have harmonics, the sine wave is a little bit broken up. It's still going to flow up and down, but it's going to have these static almost points, and this starts to create a lot of heat in the circuit. All right, that's what they mean by harmonic flow. But again, this is only when you connect power to a piece of electronic equipment, and it has to be a lot. Like for example, one computer connected to this circuit is not it is generating harmonics current. Again, it's just a name for current produced by electronic equipment, and only because it is not a clean sine wave current. Now, if you have a lot of computers on a circuit, right, if you're looking at a data center or, you know, all these Bitcoin mining places and anywhere you have massive computer systems connected to the power, then yes, then you have these really extreme harmonic currents that could really put some damage on neutrals. So they actually make these things called harmonic filters that would go, like basically the power, instead of going straight to the panel, it goes into this harmonic filter and then it goes into the panel. And as the crazy harmonics are produced from the branch circuits, before that current gets back over to the main panel, it gets ran through a filter and then it cleans up the sine wave. I've only worked with it once. It was in a computer room for a television station, and I installed a couple of them. Nothing fancy, you just bring 3 wires to one point, 3 wires to another, and it works basically like a transformer when you guys get into wiring those up. So nothing crazy, but I did want to explain harmonic current because it is there, so in case there was a curiosity. And then number 3, right, these are all things that are producing temperature and could limit the conductor's temperature rating. The rate at which generated heat dissipates, gets out of, and into the ambient medium. Ambient medium is whatever is in the area. This conduit could be outside, so as the heat dissipates, it dissipates into the air, or it could be in concrete. And how do you, right? You're buried in concrete. Here's a conduit. Got a bunch of wires inside this conduit. Where is this heat dissipating to? It's not. It's heading out and only out of the areas where this conduit pops up and goes into a panel, junction box, or whatever. So that's what they mean, the rate at which generated heat dissipates into the ambient medium. Thermal insulation that covers or surrounds conductors affects the rate of heat dissipation. In other words, the type of insulation, the type of conduit, the area the conduit is in. Again, if the conduit is sitting on the rooftop of a building, heat can dissipate pretty good there. But if the conduit is buried underground, heat doesn't dissipate at the same rate. So these are all factors that are considered when, and this is going to be kind of a part that we're just going to work with some numbers, but when a designated temperature is established for the conductor's run. All right, because you could think, well, the conduit is inside this building. All right, this building is just a regular building, temperature controlled, so it's, you know, whatever, 75 degrees on average. How can these wires be dealing with a lot of heat? Well, depends. If you use a rigid conduit, it's thicker than EMT, so that's already one of that down here. The insulation that covers or surrounds the conductors is going to affect how easy the heat can get out of this. Again, if the conduit is buried underground, then you can't get out of it. So once a heat temperature is established, as far as what this conductor is going to deal with, then we can start to do our calculations. All right. So let's jump over to the temperature or ambient temperature correction factors. First thing again to point out, just a reminder from yesterday, this takes effect the second we go above, right? As soon as the heat factor goes above 30 degrees Celsius or 86 Fahrenheit. Just as I was mentioning, the amperage for those conductors in 31016 is based off of 3 current carrying conductors in the conduit, no more than that. The same thing for the temperature. The temperature is based off of 86 degrees Fahrenheit or 30 Celsius. Now we have 2 tables. Let's just look at the table here. It says for ambient temperatures other than 30 degrees Fahrenheit, multiply the ampacities specified in the ampacity tables. In other words, multiply the ampacity of the conductor by one of the appropriate correction factors shown below. In other words, the numbers that you see down here, specifically in this block right here, are multipliers. All right, technically they're based off of, these are all percentages. All right, so for example, this is 129%, and if we go down here, this is 50%. But they are giving them to us already with the, all right, if we have a, whatever, we have 129%, then the way to turn that into a decimal is you move the decimal, and then it becomes 1.29, if you don't remember that little situation with percentages. Anytime you want to multiply or divide with a percentage, you just move the decimal 2 places, and there you are. Now, a few things that we have to consider about this temperature rating correction factor. One is, what type of wire insulation are we talking about? Now, this can land in our plate in 2 ways. If you'll remember from Code A, there was a rule that said 100 amps or less, you have to use the 60-degree column to select your wires. This is in 110. Yeah, 110. 101, technically 100 amps or more, but 101 amps or more, then we pick the wires from the 75-degree column. So this is one way where we have to just simply deal with the wire that we're using. But I'm not going to make it that complicated. All right, I'm not going to go into any kind of load calculation first, then try to figure out whether we're 100 amps or less or 100 amps or more, and then start going into the temperatures. Instead, what we're going to do is we're simply going to say, this is the insulation type we're using. For example, let's say we're using a number 10 THW. The first thing we have to learn how to do is find the ampacity of that conductor. And the way you do that is by heading over to table 31016. Now, unless otherwise mentioned, every wire is going to be copper, unless the question says an aluminum conductor, which it potentially can. But we would come over here to the temperature, to table 31016.
35.
Say again, 75, correct. This is our table because there is THW. And sorry, did you say 35? Yes.
Yes.
Correct. 35 is the amperage for that wire. So that's the first thing you have to learn how to do, is simply find, and see what I said about 60-degree columns, only two insulation types. So not a lot comes out of here, except sometimes we're selecting the conductor from here, but we don't want to go down that path just yet. So that's the first thing that the question is going to say. It's going to give you a wire with an insulation type, and so we find the ampacity of that conductor. Again, that ampacity is solely based on the fact that this conductor was tested at 35 amps. It held that amperage without any loss of strength on the conductor at 86 degrees Fahrenheit. Now, 2 things can happen to this wire. One, this wire can find itself in colder temperature, right? We're getting ready to go into the winter months. It's 45 degrees this morning out here in Tennessee. If the temperature is colder, right? Look at where we're at here, 50 or less, 45 this morning over here. So if the temperature gets colder, in fact, the wire can hold more amperage. All right, the wire has an ability now to hold more amperage. How do we know that? Well, we would take, I just want to make sure everything is on screen. We would take 35 and we would multiply it by the correction factor for two things. One, we're looking for the temperature, so we're working with, let's just use the temperature I just mentioned, 45 degrees Fahrenheit. So they don't have a spot for 45, but it's less than 50, so here's where we're at. We're at the first row here. We don't use the 90 degree because it's THW. We don't use 60 for the same reason, so we use the correction factor out of the 75 degree column. So the correction factor here would be 1, or 120% if you wanted to look at it that way too, which is the correct way to look at it. So in other words, I get 125% more amperage from this wire. All right, 35 amps now becomes 42 amps. If I multiply it by the 120 there, I'm just going to write 42 down here. If you can't see that, what I'm writing is 42 amps there on the bottom. Should be able to, but I think sometimes the bottom right of the screen for you guys has some stuff in the way. Don't worry, I'm going to take a whole page now and we'll work out some stuff. All right, good so far? Any questions? Now, usually, go ahead.
Where does the 45 degrees come into play?
Oh, that was just the temperature that I said we were dealing with.
Okay.
So it's like wherever you're located.
I just use that number as reference point. It's based off a few factors. Again, the length of this conduit run is going to play a role in the heat temperature factor. Where this conduit is it in free air? Is it not free air, but the conduit itself? Is it outside? Is it buried under the ground? All of these will take us to a temperature. Go ahead.
So the variation in temperatures depends on what we multiply by. So let's just say it was 106 degrees outside. We would use 0.82 instead of the 1.2.
Exactly. If it was 105 degrees outside, I think that's what you said, or 108, then yes, we would change the correction factor based off of that temperature.
Okay.
Now, here's what I don't want to confuse with, because you could be thinking, well, wait a minute, it's not 105 all the time outside. Also, is it the 105 that we're looking at, or is there another temperature that we might be thinking about? And here's where it gets a little bit tricky with the temperature, because the temperature needs to be established by some method of figuring out temperature factors. Usually this is done on the engineering side of things, because it's not so much it's 105 degrees outside, is what's the temperature inside the conduit? For reasons of amperage is going to create heat. So you take a page here. I got some wires running through here. All right, and current carrying, meaning the ground does not count, the neutral counts, and the hots count. All right, so let's just make this one's a hot, this one's another hot conductor, this is a neutral, and this is another neutral. Actually, it's a good idea for us to simply write grounds do not factor in. All right, so the ground doesn't factor. In fact, there are other situations that don't factor in either, where what if these are all non-current carrying conductors, like for control voltage systems, which probably not aware of that, but control circuit wires don't carry any amperage. They're just energizing, turning things on and off, like making, just sending voltage to and from places. They don't handle a load. Well, if these things are not current carrying, then we ignore them, just the same way as we ignore the ground wire, because it's not a current carrying conductor, ever, ever, ever. Now, you said 108, so let's put, 108 outside. But that's not the temperature inside the conduit. And also, that's not the temperature inside the conduit because of the amperage that the wires are going to be handling. What if these are high amperage wires? All right, what if each one of those wires is handling 100 amps? That's generating an amount of heat in here, along with the outside temperature, along with the fact that the wires are confined to a conduit that doesn't have a lot of space to get rid of the heat. As I mentioned, the front of the conduit, or the points where the conduit's going into a junction box, those will be points with less heat, but this temperature has to be factored in from the hottest point inside that conduit. So all of this is engineered out. Right? All of this is determined through engineering factors that are a little bit outside of our wheelhouse as far as what we have to do to make these correction factors. Now, there is an attempt to make all this stuff. There is, right, we can get into the engineering, as I mentioned, the engineering of the temperature. These are some formulas that are just outside of our wheelhouse. Conductor temperature, you have resistance at one. There's a lot of ways in which this gets factored out. All we need to do is land at a number that we've designated for the temperature that the wires are dealing with, and then know how to run from there. All right, so when I say 108, it's simply that's the temperatures the wires are dealing with whatever factors could be presented for the wire. Again, that wire goes underground, it gets even hotter for that 100 amp conductor. So what we will have for questions is just something like this. Number 10, I'm just going to put what we just did right now. THW, ambient temp of, and let's use your 108 Fahrenheit. And now the question, there are two questions to this. Question number 1 is, what is the adjusted ampacity of the conductor? All right, the adjusted ampacity of the conductor. To know what the adjusted ampacity of the conductor is, you have to start by knowing the initial ampacity of the conductor, which we said was 35 amps, and correctly said it was 35 amps. So now let's run these numbers together. All right, again, we come back over to our table. Now, as we said, we look for 108 degrees Fahrenheit. This is, I can't really highlight too well with this PDF. It doesn't let me just perfectly highlight. But you can see 108 would sit between 105 and 113. And as you mentioned correctly, our correction factor would be 0.82.
So 35 times 0.82.
Exactly. 35 times 0.82. And now we would have the adjusted amperage. All right, so anybody got that number? I can do the math too.
28.7.
28.7. Okay. All right, we could probably just say 29. Now, realize what happened. I started with a wire that can hold 35 amps, but this wire is sitting in a 108 degree temperature situation, and therefore now I've lost, what, 6 amps off of that wire, which is what this 82 is telling me. This 82 is based off of 100%. So when you see 82%, it means that I've lost 18% of that wire. All right, that's what that factors out. We lost 18% of the wire's amperage. But the way we do that is not by going, what is 18% of the wire, and then subtract that from the 30. We don't go that route. We just, real easy, we do the math this way. 35 times 0.82. But that's what that means. 82% means I've lost the other half of this that gets all the way to 100. So how this question can change, not in many ways that is going to get too complicated. I'll change the wire and I'll change the temperature. This will then lead us to a different ampacity, and of course then to a different adjusted ampacity. So let's try that one more time, just to make sure we got it. Or we can try it a few more times, doesn't matter. However long it takes. In fact, let's change. Let's go with a 1/0. Let's go with THHN. And let's go with an ambient temperature of, actually, let's change it up a little bit. Let's go with an ambient temperature of, who do I want? I get ambient temperature anxiety of picking the right number. 47 degrees Celsius. All right. So I'll pause here, let everybody try to figure this one out. Remember, find the ampacity first, find the correction factor, and then multiplies.
47 or 49.
49?
No, the intent. It looks like is it a 7?
Yeah, sorry about that. My 7s are 7. And Celsius. And I should be out of the way as far as, yeah, I'm out of the way. So I'll go do it too, just to make sure what's going on here. All right, so let me also do this.
Thank you.
Ends up being, oddly enough. All right. All right, so I'll put first the ampacity, which is 170. Right, that's the amperage that this wire can hold. And then what is the adjusted ampacity?
0.82.
Say that one more time.
0.82.
Oh, the correction factor? Okay, yeah, 0.82. So that would mean the adjusted ampacity is,
139.
there you go. 0.4, we can drop that 0.4. So we'll leave it at 139 amps. All right, any questions or follow-ups to this right here so far?
I got a different answer.
You got a different answer? Okay, let's walk through it.
Well, I put 170 amps times 0.41.
0.41, okay. All right, so getting to 170 is correct. So half the question good. So far, so good. All right, just to walk through it in case somebody's sitting in there going, I got that part wrong too. I'm not going to say anything. That's okay. I will walk us through it. 1/0, right here on the far left is 1/0. It's the first 0 of the 0s. Now, THHN, which is a 90-degree insulation.
Yeah. I just,
Yeah.
but
All
just
right, good to go. And then that's how we got the 170. Again, hard to highlight a little bit, but there's 170 there. Okay. So we got the ambient ampacity. Now, the temperature is 47 degrees Celsius, which is one of the things that I wanted to make sure you see is that we got two sides of this table. We've got a Celsius side and we got a Fahrenheit side. The numbers don't overlap, thankfully. When you get to solar, they are. It's going to be a little bit more difficult, but these don't overlap. Well, yeah, actually they do. We got some 80s and 70s, and we got some 80s and 70s over here. So they actually do overlap. So 47, go ahead.
I call my mistake.
Oh, okay, good to go. 47 degrees Celsius. Again, it sits between 46 and 50. And now the important part is that we make sure that we match the insulation type. In fact, I'll just use the table here. And that's the key to this. Sometimes your eyes will just go, all right, 47 is here. I'm just going to use that one because it's the next thing right over to it. Your eyes will take you to stuff like that. So 82 because the wire insulation type was 90 degrees Celsius. So the wire insulation type tells us which temperature column that we're going to pick the conductors from. All right, good. If you saw your error, great, because that's half the intention we're going over is if you did make a mistake, just where did I make it, and now I know how to adjust it. All right, let's try it one more time. Change the wire, change the temperature. That's it. That's the only way this can go. Change the wire, change the temperature.
You said there was 2 questions? Or was
Yes,
that-
there's going to be a second direction that we're going to go with this. That is correct. We're doing this one first, and then we'll get to the next question. All right, so let's put another conductor here. Let's go with a number 4. Let's go THWN. We'll leave it there. THWN. Let's go over to 125 degrees Fahrenheit. Now, for the exam, these are 4 questions that I could ask. I could ask, what is the ampacity of this conductor? What is the correction factor for this conductor? What temperature rating is that insulation of the conductor? And what is the adjusted ampacity of the conductor? All right, 4 questions right off the bat from just what you're looking at here. I mean, we might as well already kick into review gear since we'll be reviewing tomorrow. So you have to be able to find the ampacity first to get to the adjusted one. I think this is a wire. Yeah, that's a wire. Number 4. And so I'm going to drop that here just to make sure if anyone is stumbling across that, there is your ampacity. So number 4, THWN, which you're probably never going to find anymore unless you go to like an old supply house in some lost city somewhere. 85 amps. And as I think I was mentioning it yesterday, maybe I was saying it to the Code A class. There was like a time in the 70s and 80s and 90s where all of these insulation types were showing up. But right now in 2025, we have 2 types. And they're both on the same wire. THHN, THWN2. That is 1 conductor with 2 types of insulations. And that's the 100% what you'll find now. So, but they're still asking these questions in the code exams with all these different insulation types, so we still have to know how to do this. All right, 125, what is the correction factor? Not the ampacity adjustment yet, just the correction factor.
The 67.
What we're going to multiply, 67. Sounds good. Let me double check it to make sure. Yep, it is a bigger loss. That's what that's saying, right? The hotter this got, the more we lost off of that wire. Now we're losing what? 37%?
33.
33, yeah, sorry about that. The other half of that, yeah. 33% of the wire's amperage. So that's 108 was only, what, 2018? Now we're losing 33. So the hotter it gets, the more amperage I lose off of this wire. What's the adjusted number?
57 amps.
57?
Yeah.
57 amps. Okay. All right. Does anyone have any follow-ups to any of this? Are you struggling at any point finding or understanding the temperature of the insulation? No. Understanding where to find the correction factor based off of the ambient temperature, establishing ampacity or adjusted ampacity. Okay, good. Now let's flip this question around, because here's the other side of this question, and this is the more practical side. The more practical side is, well, what do I do then? I wanted to wire up something that is 85 amps. That's why I chose number 4. But you're telling me that this number 4 now can only hold 57 amps. So the other question is, what size wire is needed for, and then we can get into the amperage and correction factor. All right, so I'm going to leave this here because I will come back and reference it tomorrow when we review, and I'm just going to structure an entirely different question. So, go ahead.
Emilio Gonzalez is here.
Oh, thank you, sir.
Gotcha.
Let me update that. Appreciate that. Mr. Gonzalez. Good to go. Oh, they told me you were in the bathroom. All right, good, thank you. All right, so let's say we have to wire up a circuit that is 80 amps. Let's go with 80 amps. The wire now that I want to choose, this is how the question is going to be asked. What size wire is needed for, if you even want to write that down, you can. It's on video, so you can always come back to this. What size wire do I need for 80 amps with an insulation type THWN, let's say 2, with an ambient temperature of, and then we'll have an ambient temperature here of, and let's go with, let's keep it at that, let's go 110 degrees Fahrenheit.
Let's use it.
Bless you. So let me walk you through this, and then I'll give you guys 2 options on how to find this. You can choose whichever one you like, and then I'll give you some practice questions on your own. So the idea is now, I have, let's say, for example, let's just make this a panel. I'm running a conduit over to this panel. I'm trying to figure out what size wire I need, bless you, for this 80 amp circuit. But this panel happens to be in a boiler room, whatever the case is. This conduit is going to be really hot internally. 80 amps is a good amount of amperage. So inside that conduit, the temperature that we're dealing with now is 110 degrees Fahrenheit. So my goal is to find a wire that after we apply the correction factor of 110 degrees Fahrenheit, it will, remember, as it reduces that amperage, once it loses the amount of amperage, it can hold 80 amps. So there's a few ways to do this. I'm going to show you the way that it was taught to me, and then I'm going to show you the way that somebody else taught it to me when that person was more concerned with time as a factor for taking these questions in, right? So one of the ways that you can do this is to come over to 31016, right? Let's start in this direction. Let's start selecting a wire. First, we come over to 31016 and we go, all right, what insulation type was it? THHN2. Okay, there is THHN2, so it's the 90-degree column. And now I can go, all right, well, I'm going to need to cover 80 amps. So I can start somewhere here in the 95 or 115 conductor. So it'll probably either be a number 4 or a number 3 wire, right? Because 95 amps or 115, as I reduce amperage from this because of 110 degrees Fahrenheit, it'll probably land at one of these 2. So I can just pick one of these 2 and go, all right, let's go with the number 3, 115 amps. So we bring in 115 over here, and we're going to multiply that by the correction factor of 110 degrees Fahrenheit based off of the THWN's insulation, which is 90 degrees. And so we come over here to the table as we just did right now. This part should not be hard. We go 105 to 113, 90 degrees, 0.87 is our correction factor. And so that's what we're going to multiply that 115 by. And go, all right, let's see if this lands at more than 80 amps. So 115 times 0.87, 100. Okay, 100 is, and 0.5, so we can drop that. So right at 100, that's a perfect number. Now, could I find a smaller wire? Maybe the wire right before this was 90 amps, the number 4. So maybe I can try that. Because we always want to find the smallest conductor needed. That way the cost is not too expensive. So,
Isn't it 95 amps?
was it 95? Sorry about that. I forgot. I thought it was 90. Yeah, 95. Sorry about that. Thank you. Thanks for making that correction for me. 95. Apologize on that. Sorry, let me run the math again. 0.87. So 82.65. So good. This is the better wire. In fact, the questions will always be, what is the minimum size conductor for this load up here? Minimum conductor size. So that is the minimum conductor size. What was that? That was the number 4. That number 4 starts at 95 amps. It does reduce, but not by a lot, only 13%. So
pretty much we get the like the 115 and the 95, and we just multiply by the ampere of the 110.
by the correction factor for 110, yes. By the correction factor for 110.
And that's how we found the minimum.
And this is how we found the minimum of 82.65. But I want to point something out, because I'm going to show you another way to do this, and then you can pick whichever one you like. There's 2 ways to get to this answer. You'll notice that for this to go correctly, I did it twice. Right? I did the 115 times 87 or 0.87. I got to 100. I go, maybe there's a better one, so let me try the number 3 at 95 amps, and then I got to 82.65. And I recognize that this is the better choice than the larger conductor.
Nice.
I had to do the math 2 times. The other thing that we were able to do, we were able to go, well, 80 is the starting amperage. Let me go right above 80, 95, 115, and let me start to work my math out. However, I'm going to change things a little bit. We're going to keep this 80. The only thing I'm going to change here is the temperature. All right, I'm going to make this now crazy hot. All right, let's go with a high temperature. Let's go with, it still has to exist in the table, so that's why I have to look at this table. Let's go with 152 degrees Fahrenheit. Okay. If you now go to the table with the wire amperage and work your way down and come up with the 115 like we had, or the 95 amps. Let's put the wire size here. This was a number 3 or a number 4. If you go this route now and you go and find the correction factor for 152 degrees Fahrenheit, remember it's a 90 degree column conductor. 152 degree Fahrenheit falls between 150 and 158. So 0.58 is now our correction factor, meaning we're almost losing half of the entire amperage of that wire. Almost 58, so 42% of it. But that's a lot. You can multiply either one of these that you want to do by 0.58. And we can do both, just so you can see the resulting numbers now. All right, if we take that, let's go with even the higher number, 115 times 0.58. This drops us all the way down to 66.7 amps. That's not enough to cover 80 now. Forget the number 4, 95 for sure won't do it now. So now I got to go back to the drawing board. I got to go back to the wires and go, all right, number 3's not cutting it. Let me try to jump to another wire ahead. Let me go to the number 2, or maybe let me go to the number 1. All right, let's go over to the number 1 conductor now, which has an ampacity of 145. All right, I want to make sure I'm not going too fast and everybody's following where I'm at. 145 now. And I will run it through this correction factor of 0.58. And maybe it is. And we land at 84 now. Okay, so we found the wire. Number one, it will cover 80 amps once it loses 42% of its amperage and drops down to 84. This will cover the 80 amps. But you saw how many times we had to do the math now. I started with a possibility of a number 4 at 95 amps. If I would have I ran that math way too small. The number 3, run that math way too small. If you got to go back now to table 31016 and look for another conductor, what if I would have picked the number 2 at 130? I would have calculated it. It would have been too small. And now to assure myself, I would have done the calculations for number 1 and figured out, finally I got to the right answer. So there's an easier way to do this, but you have to remember something about the resulting number. But first I want to pause here and make sure that everyone has followed my train of thought so far. In all of these cases, I have started with select the wire first and see where it lands at the end after you multiply by the correction factor. Instead, let's go a different route. And I'm going to change this. And I'm going to change this just to play around with some new numbers here. Let's say I got a panel and I got to wire this thing up. Let's go large scale amperage. 150 is actually not large in the grand scheme of things. When you think about the largest breaker being 6,000, this is way small really in that world. But let's put this temperature at a high temperature again. We're keeping it THWN. So that means I can go even higher temperature than 152, I think I put there. Let's go even higher. Let's go with 170 degrees Fahrenheit. And here's the thing. The thing is, when you get to these high temperatures, now you can't just go, it's not as easy, I should say. You can always do the multiplying that I just showed you. But it's not as easy to just go to the table with the wire amperage and go, all right, what's the closest wire to 150? A little bit above. And then start running it through the correction factor, because it takes time to eventually multiply out to the right number, like you saw us do right now. That's how it was first taught to me. Because the first person that taught it to me wasn't concerned with time as a factor. They just wanted me to learn how to find the conductor. But then I took a journeyman preparation course, and this course prepares you for the journeyman exam. And one of the things they focus on is easier methods to find answers that reduce the amount of time it takes you to find the answer, because you are going through a timed exam. When these temperatures get really high, like 170 degrees Fahrenheit, I can't just go over to the wire table and find a wire close to 150, because I'm going to be multiplying a lot. I'm going to be losing a lot of amperage. All right, we can go for THWN, keeping in mind that it's a 90-degree column wire, right? 90 degree. If we find 170 degrees way down here on the bottom, 0.41, I'm going to lose a lot of that wire now, right? 59% of this wire's amperage is gone. So whenever you have these high numbers, high temperature numbers, the better thing to do is start by finding the correction factor. So I'm now going to write this as a step to find these answers. Step 1 is, whoops, I was going to write step 1. Find the, and I'm just going to put CF, if you want to spell that out for yourself, correction factor. All right, step 1 is find the correction factor, which we just did. Again, 90-degree column, 90 degrees Celsius column. 170 degrees Fahrenheit, we match those two and we find 0.41. All right, so step 1, find the correction factor. Step 2, and this is where this gets, for me, the easiest way to do it, is divide it by the goal amperage. What amperage do I want to cover? In this case, 150. So now let's go ahead and divide that. Do not forget the decimal. But divide 150 by 0.41. And you'll get to a number of 365.85. So I'm just going to make that 366. Make sure you're dividing this out so you can see the number result. All right, it goes way out there as far as after 365.85. So I'll write that as step 2. Step 2. Divide by amps. All right, if you want to write that out, divide by the current or target current or however you want to, grow that note a little bit. But keeping it short like that, for me, I've also done this enough so I know what I mean by my shorthand here. So if you need any, more explanation to that, write it out for yourself. But find the correction factor and then divide. You can also divide the correction factor by the amperage, if all of that helps. And now part 3. Step 3 is easy. Next size higher. That's the only part to this that you're going to have to remember, which is whatever conductor you pick has to either, which is never going to happen, be 366 amps, which we're not going to probably find that. It's very unlikely that you'll land at the number, or the next size higher conductor. So this would make the conductor A 400 kc mil. Because if we look at 400 kc mil, on the 90-degree column, which is right here, 90-degree column, remember, it's the last one over here. We work our way down. 360 is our target number. 350, too small. Happens to be 350 kc mil for 350 amps. Isn't that convenient? It's the only one. So we got to go to the next size higher, 380, which makes it a 400 kc mil. Now look at how far we've come from 150. 150, I probably would have selected the 170 wire, maybe the 195. And I would have done the math for those two and gone, nope, and kept going. And would I have started with 400 kc mil? No way. So the dividing one is only one step. Step 1 is really, and after that, just divide and go ahead. Find the correction factor for the temperature you're dealing with, divide it by the target amperage that you want to cover, and then whatever this number is, a wire that is that number or the next size higher, which is probably more likely the case. I remember when I was taught this, I was like, whoa, I'm going to go this route all the time. Now, when would I multiply? I would multiply if this number here for temperature was, let's say, 100 degrees. Well, 100 degrees Fahrenheit is not going to change. There I would probably not even need to do math and go, it's got to be the 1 odd. Right? Because 1 odd is 170 amps. 100 degrees Fahrenheit is not going to change the temperature much. And so I would do that quick multiplication, because either way I got to find the correction factor, and just to assure myself that I'm right on the number 1. When do you want to do the divide? When the temperature gets very high, like we had here at 170. So for that reason, just always apply the divide system. And that way you don't have to worry about, is that temperature a little bit? Is that temperature too much? What is a little bit Now they're talking Celsius. I don't even know what that is. All right, I'm going to erase this and give you guys an opportunity to find a conductor. All right, so the target amperage that we want to cover is going to be 200 amps. All right, we're going to find a conductor that's THW for it. Don't know why we would do that, but we are. And then the temperature we're dealing with here, I'll give it a midway point. Nothing too much, but nothing too little. Let's go with 135 degrees Fahrenheit. By the way, I'm keeping this to Fahrenheit, but Celsius is going to work just the same. I just know the Fahrenheit's more, so I don't have to go look at the Celsius table right now. All right, so remember the way this is going to get asked. What is the minimum, remember that, minimum size is what we're looking for, conductor for this. Because you could always go bigger. You can always say, all right, that 400 kc mil, I'm just going to go with 600 kc mil, and fine. The code does allow us to go larger for the conductor as long as wherever you're about to terminate this wire to can accommodate that wire. Which is why you can't run number 4 wire to an outlet voltage drop, because it's not going to be able to handle it. So you can always just run number 4 every time for voltage drop to an outlet. All right, I'll pause here, and again, either direction you want to go, multiply to it or divide by it, and you're all set. All right, anybody got a size conductor?
250 DC mil.
250 kc mil?
500. I got 100 kc.
All right, 250 kc mil, one person. We also got 500. All right, anybody got a different number? I don't have a number yet. I'm gonna walk through it with you guys together. All right, so 250 or 500. These are expensive between the two. So step 1, we're gonna go with the divide system. So find the correction factor is our step 1. So I'm gonna erase that, and we'll see who won out of those. So step 1 is find the correction factor for not only 135 degree Fahrenheit, but for the correct temperature rating of the conductor. So we're in the 75 degree column. Make sure that you know which column you're in, because that could be a confusing factor. 135 puts us right down here, 132 to 140, and so our correction factor is 0.58. By the way, just because I'm seeing them now, these little lines simply mean that we don't have a correction factor for this level of temperature for conductors in the 60 degree column. We don't have this level of correction factor. As you can see, it starts to get too low, and they're like, nah, these wires, use something else. 90 degree column can go into Antarctica. So 0.58, make sure you got to 0.58. Maybe that could have been the reason why we have different answers. Now we're going to divide by 200. That's our target amperage. So we just have to find the correction factor first and then divide by the target amperage. 200 divided by 0.58 gives us 344. Oh, it's almost similar to the number we had over here earlier. 344.82. So now we head over to the 75 degree column of table 31016 We work our way down until we find a wire that can hold either 344.82 amps or 345, or the next size higher. And that is going to be 500, 380, 500. So 250 kC mil would be too small. It can only hold 255 amps. I need it to, at minimum, hold 344.82 or 345. So next size higher. Alright, we're not out of the woods yet. We're going to try that one more time since I had a few folks, or just one got it wrong, but I want to make sure that person...
Exactly.
He left?
No,
Oh, okay. Yeah.
I got mixed up.
Oh, okay. Do you know exactly where then? Alright, great, great.
Yeah, I see where I did.
Alright, good to go. That helps. If that's the situation, then we're good. Now, different from this one. This one is always multiplied. Here's why that original teacher, also it was my probably first year in the apprenticeship, and that teacher did not want to give us two methods here. Because then now I can come up to this question, pressure of an exam, forgot my thing, and now I divide here and I come up with a weird number on this end and not correct anymore. So this is why they just said, let me just teach you only multiply, and now you can't get messed up. So keep that in mind. Divide is only when we're trying to actually find the conductor size. When I've asked you what is the ampacity adjustment or adjusted ampacity, then for sure we're only multiplying, no other means to get here. That's why I kept this and didn't erase it, because I just wanted to show the difference between the two. This is when I'm trying to find the adjusted ampacity, always got to multiply to get there. And this is when I'm looking for a wire size, which in my opinion, the best way to do that is going to be to divide to get to the answer. If you don't want to get confused, I'm just going to multiply the whole way through. You're probably going to be 100% okay, because multiplying just might mean that you have to do it a couple times till you get to the right size wire. And to be honest, in my first years and stuff like that, I probably like that comfort. I like to just go, I'll just keep multiplying till I get there. I don't want to confuse myself. But as I gained experience and I was ready to take the journeyman exam, then divide was now something that I can factor in.
So this method of dividing just for conductor size, but also gets the answer for the other.
It's only to find the conductor size. No other applied method to this. The multiply, this is the one that can go either or. You can find the adjustment ampacity, or you can find the conductor, but like I said, you might have to do it a few times till you get there. Now, the only other things that I'll point out, the question could add a few things, like it can say aluminum wire. Okay, we're in aluminum now. So now just make sure that unless otherwise specified, if it says aluminum or aluminum copper clad, then now we're finding the ampacity from this side. Insulations pretty much stay the same. There are a few different ones. You'll notice not as many in the 90-degree column, not as many in the 75, but same for the ones that go underground. That's what these 60s for. TW and UF is underground. I forget what the F's for. So that's one thing where we could be looking for aluminum. And again, always keep in mind Celsius versus Fahrenheit. Insulation type's going to tell us which column to go to. Shouldn't be too difficult from there. All right, I want to wrap this up with the MC Cable article. So tomorrow we'll come back to this and we'll look at adjusted ampacity and temperature correction. Adjusted ampacity and conductor size one more time. All right, and for future, and by future I mean next week. We're going to do this again next week. All right, we're going to do this again next week, but now we're going to introduce a different set of parameters, which is too many wires in the conduit. It's all the same method of situation. We're going to establish what percent, how many wires we got in there, reduce the amperage of the wire by one of these percentages, And then look at the question in the other direction, which is, okay, I got 10 wires in there. How can I have these 10 wires cover the amperage that I need? All right, and then it gets super duper when I go 5 wires in the conduit and 125 Fahrenheit. 2 correction factors. So we'll get there. All right, that'll be more towards the final. Now, one of the ways to avoid that is just don't put all the wires in the same conduit if you're going to deal with the temperature. But the journeyman exam doesn't do that for us. It doesn't go, all right, I'll make this as easy as possible for you. It's going to throw chaos at us. All right, so also to add, if anybody wants to do some of this math after class, just because I want to move into this last article, there's not a lot to cover, and we should be fine to cover it in the next 18 minutes. Please feel free to hang out after class, and I'll throw you a couple more sample questions. With that being said, we're going to jump over to Article 330, which unfortunately I did not have the page here. I usually like to have the page for you guys, just so we know where we're headed. But I'll find it.
220.
Thank you very much. 221. All right. Page 221. Okay, so you guys have been, another reason why this shouldn't take us too long is because you guys have already been working with this conductor. Everybody knows what MC cable looks like. All right, now, one thing to point out is that there is a cousin to MC. And it's called AC cable. AC cable, or armored clad cable. Armored clad cable. This one is metal clad cable. The other one is armored clad cable. It's just like Romex is NM, but we call it Romex. AC cable is actually called BX. All right, for where they made it, which was the Bronx. And if you go into the state of New York, mostly Manhattan, but everywhere else as well, there is no MC cable. They use BX. And the difference is the outside metal is much more durable. It's a stronger metal outer coil. So AC cable is a lot stronger than MC cable as far as things running into it, or what they call severe physical damage or physical damage. It can take a little bit more physical damage than MC cable can. The only big issue with it is just heavy. It's a heavier metal conductor that's ran in the same way as you guys run your MC cables. Usually when we're running through metal frame, if you didn't notice that from your code A to your B, wood frames in code A, metal frames in code B. Metal frames, not a good idea to run Romex. We are allowed to run Romex through metal studs. You just got to use bushings and gromming and all these other protecting factors for that conductor, for the Romex. So when we're in metal, we like to use a metal flexible cable. And MC is the new type that everybody's using. And more specifically, and the biggest factor difference between is that AC cable has a bare copper ground. A bare copper ground like Romex, whereas MC cable has that insulated ground conductor, which we just prefer a lot better for this conductor. So it's lighter weight, it's got that insulated ground, it's just become the industry standard that everybody's using. But there's another type. If you ever run into it and you try to do the old break it with your hand in half and you cannot do that, this thing is made out of steel, and forget about it. You're gonna have to now cut it with your hacksaw. Even if you use the rotor splitter, it is a nightmare. 3 turns cutting that cable and time to change the wheel. So hacksaw is the way it goes. So it takes a little longer also. All right, so just let's jump into this article, MC cable, or again, metal clad cable. It is a cable, and what we know about cables from the code book, just like NM cable, is, if you did not know this, I'll point this out, which is it comes with the wires, all right? Wires included. Anytime you see the word cable for a conductor in the code book, this means the wires are coming with it. MC cable, AC cable, NM cable. So that's what this article is on. This article covers the use, installation, and construction specifications of metal clad or MC cable. All right, type MC cable shall be listed for fittings and all that. So the other thing you got to know about MC cable is that you got to make sure you're using the correct fittings for it. A lot of people try to get away with some fittings that aren't for MC cables. They're not using the red little bushing that goes with it. Redheads, they call them sometimes. When it comes to conduit, there's only 3 things you got to know about the conduit. And this goes for any article section for conduits. Where can I use it? Where can't I use it? And how do I install this thing? There's a 4th, which is there any extra about this conduit specifically? Like if it's PVC and it's plastic, it has some little extras about it. RMC, rigid metallic conduit, has a few extras about it. So for this one, we'll look at those, but we'll start here as far as uses permitted go. And basically almost everywhere. All right, the only place, and keep in mind, just think, this is why I get to this when you guys have already seen this conduit. Think about the conduit. Can I put this in an area where it's going to get wet? Probably not. Right? You might think we can't, but we can. MC cable can go outside. You just have to make sure you use the type that is allowed. So if you look at from the uses permitted, we'll go through a couple of the ones. You know, you don't have to memorize these. If I were to highlight, I would just highlight uses permitted. I might highlight a couple that I think were important, but other than that, I would just highlight uses permitted. And if a question comes up as far as, can I use MC cable here? I'd come to the uses permitted and see, yes, I can, no, I can't. So we'll run through some common ones for feeders or service or branch circuits. Anywhere coming into the panel, feeding the panel, or for any of the branch circuits leaving the panel. All right. More than likely they'll be used as branch circuits, but I have seen MC cable come in as feeders. For power, for lighting, for control circuits, for signal circuits, for indoor and outdoor use, so you can use it outside. Exposed or concealed, this means I can expose it so you can see the MC cable. If it's in a warehouse or something like that, I can definitely run MC cable exposed. Or concealed, meaning I can put it behind drywall, which is a very normal way to do it. To be direct buried where identified for such use. Right, and we can ignore the cable tray in a conduit, so I can put it in a conduit. Aerial messenger, you don't have to worry about. Damp locations, wet locations. Keep in mind, like always, whenever we get metal into damp or wet locations, there is corrosion to worry about. So this is where, for outside use or for direct burial, there's going to have to be some considerations, which is probably you're dealing with damp or wet locations at that point. And you have to have a corrosion resistance jacket for that conduit, which is why we don't use it as much, if ever. I don't think I've ever seen anyone bury it or put it outside. For that reason, you just go with something that you don't have to worry about adding any extras to. Like PVC, perfect. It's plastic, put it outside. No corrosion, no, where it's plastic, it's not going to corrode. All right, so that's uses permitted. Just to go over to the code section, there are a couple of extra things when we get into the cable trays, which you don't have to worry about. Cable trays usually carry low voltage data conductors for data communications like internet and phone. Direct burial has a section that we would have to consider if we were going to put it in the ground. So we'll jump over to the next section, which is where can't I use it? Always that for conduits. Where can I? Where can't I? So where can you use it? Where it's going to be subject to, this is where AC cable comes in. AC cable, yes. MC cable, no. It's made out of aluminum. You bang that with anything and it's going to get squished, and more likely it's going to, what they're worried about, going into the conductors and damaging the conductors in some way. So number one for MC cable, cannot use it if it's subject to physical damage. Now, that is one of those code things where, like, you might ask, well, what is subject to physical damage? What if I don't deem this as a situation where the wire is going to be subject to physical damage? Well, it's going to be up to the person that can decide that, which is the authority having jurisdiction of it. If you're not getting inspected, then, you know, we use our most common sense for the situation that we're wiring something up. All right, exposed to any of the destructive, corrosive conditions in A or B, direct burial in the earth or embedded in concrete, unless identified. So you have to make sure that you're buying MC cable that is identified for direct burial, or which means going directly into the ground. Whenever they say direct burial, it means this thing goes in the ground. It doesn't go in the ground in a conduit, it goes in the ground itself. Or embedded in concrete. You have to buy the MC cable that is rated for going into concrete, which is not the one that you guys are using right now. Exposed to cinder fill. Cinder fill is not something that they use anymore. This was a way to, if anyone knows anything about concrete, these days for concrete they're putting gravel. Right, you put a bunch of gravel on the floor, and then you can either put plastic over that, or you can pour concrete right on top of the gravel. These days we're using gravel, or more likely they'll use gravel. Cinder fill was that. Instead of gravel, they used to have this stuff called cinder fill, and it was just a bunch of different not chemicals, but it had a bunch of different properties that could corrode the conduit. If the conduit was, for example, all the cinder fill was here, now you lay your concrete conduit on top of that, and then they pour concrete all over that conduit. Because your conduit is now touching this cinder fill, it could corrode it in some way, or the properties of the cinder fill could mess up the conduit. But these days we don't use cinder fill. These days they use gravel, so you can throw your conduit right on top of gravel. It's one of the reasons why they go with it. And then all the other things you see here, like strong chlorides, caustic alkalides. These are all chemicals, vapors of chlorine or hydrochloric acid. Basically, any kind of those hazardous chemical situations where it can destroy or eat away at the metal of that conduit. That's the big thing with it that they're worried about, is the conduit getting all destroyed. All right, all of this stuff here, the reason why I'm not emphasizing on it, not to say a question might not show up from it, just that this is like Romex, all right? It follows a lot of the same parameters, all right? So you can go through parallel framing members. It can be exposed. Don't worry about the bending radius. I will not ask a question from here. It gets into some math that we don't have to do, like 10 times the internal diameter. We're not going to run into all that. All right, inaccessible attics. Like if the question says, can I put them in attics? Well, then you can find it in these code sections. I'm hitting the important ones, which drops us down to 330.30, which is how to support this thing. And if you ask me what's the most important thing about knowing about running conduits, is how to support it. Because here's the thing, the blueprints are going to give you the conduit that you're using. So you don't have to go into this, can I use it, where can I not use it? It's in the blueprints, we're using it, good to go. That's it. The engineer said we're going to use this conduit, whether it's EMT or NM or MC or whatever. It's in the blueprints, we're using this one. This is a choice always made in the field. This is never, ever, ever on a set of blueprints. How to secure and support the conduit is not on the blueprints. So these are the questions that code exams are going to ask you, because these are field choices, and because you're going to make this choice on your own, they really want to focus on whether we know how to do those or not. There's other areas of the code book like that too. So securing and supporting, first thing I want to point out is that these are two different things. All right, securing happens, if you want to write this, you don't have to, but just something to know, whenever you're going into a box or you're leaving a box. That's when you have to secure. All right, it's the same. It's just that the code book's making a distinction between the two, so we should also. All right, now going into a box, going into a panel, going into a machine, going into a motor, leaving a panel, leaving a junction box, leaving leaving anywhere, like I pointed out earlier, that's a pull point, anywhere where I can access wires. So I'm just gonna put a junction box here, and we've left with the MC cable. There's my MC cable. Numbers that you have to remember are very important. 12-inch. Unless otherwise permitted in this code, cables shall be secured at intervals not exceeding 6 feet. We're going to get to that number in a second, because it actually comes over here in support. But for securing, the next part of that, cables containing 4 or fewer conductors, sized no larger than number 10, so this is our average for residential use and commercial, shall be secured within 12 inches of every box, cabinet, fitting, or other cable terminations. One easy way, again, to just call all those things is a pull point. So within 12 inches, I got to put a strap. Does it have to be at 12? No, it could be at 8, it could be at 6, it could be at 1 if you wanted. But the max shall not exceed, right? Or as it says in the code section, within 12 inches. And now from there, unless otherwise permitted in this code section, now reading C over here, this is where I said you don't have to worry about this one just yet, because it's going to come over here, shall be supported at intervals not exceeding 6 feet. So the only thing the code doesn't tell us is 6 feet from where? 6 feet from the box, so I measure 6 feet now, and then within 6 feet the next strap? No. It is from the last support wherever you put it. If you put it at 1 inch, then 6 feet from that 1 inch. If you put it at 12, like this one, then 6 feet from that one, within, or in other words, shall not exceed, which gives us again sort of a within. So I can put my next support right at 6 feet, or at 4, or at whatever, but whatever that one is, if this cable is running longer, then within 6 feet of that one as well. So usually what people do is they establish a system for themselves. I strap this at 12, and then I strap this at 4 feet, and then 4 feet, and then 4 feet, and then 4 feet, and then I'm getting close to a box on the other side. We can slide over and continue and continue and continue, and now I get to the box over here. And like I said, within 4 feet, within 4 feet, and then within 12 inches of that box. And this one is a tough one, because what if I've ran it and I'm at 18 inches from the box? No, you still now have to put another one here. So still have to be within 12 of this box here, and within 12 of that box there, even if your other supports are landing pretty close to this one. Still have to now consider, and I have seen them fail inspections for that. They are sticklers for supporting on the conduits. Now, last thing, 1139, I landed this plane perfectly. We got one last thing to talk about, which is, and this is only for flexible cables, and that is, sometimes with the flexible cables, I don't have to support them at all. So 1, 2, and that's it. We're not going to worry about 3. All right, so we'll ignore 3. And we have, 1 is not really giving us a number. 2 is going to give us a number of 6 feet. But 1 is fished, not finished. That is fished, pulled, fished between access points through concealed spaces in finished buildings or structures, and supporting is impractical. All right, like I'm pulling it through a wall. It's already a finished structure. I cannot get into this area to support this. Well, all good. We can just pull it, leave it unsupported. This one is the more likely that you'll run into this situation, although the first one maybe, but in almost all construction circumstances, you're going to be putting in light fixtures. And these light fixtures come with what we call a whip. All right, the whip is the MC cable that is coming off of this luminaire. And this MC cable will be exactly 6 feet from the manufacturer because of this code section. which says, I don't have to support MC cable if is not more than 6 feet in length, that's why they make it that way, from the last point of the cable from here to here, to the point of connection to the luminaire, to the light fixture, or other electrical equipment that the cable and point of connection are within an accessible ceiling. So only in the ceiling. So 3 things that we want to point out there. First, 6 feet in length. Second, in the ceiling. And third, connection to lights. All right, it's 11:41, so I'm